Yes.
May I present in English?
Yes.
It's better this way because everything is in English here. So, Professor Prishlyak, I'm glad to see you. I'm starting my talk. Is it okay?
Okay.
So, at last, I managed after some little technical problems to enter, and I'm happy about this. And I'm happy to see familiar professors, which I know for a very long time. And the title of my talk is here. It's all about organizing big data, ultimately, which are primarily displayed and registered as tensor type data. So they are massives and arrays of data which are indexed. And what is important is that the indices compared, for instance, with differential geometry are not necessarily ranging through the same range of numbers. So it is not the same range for each index. There are various indices and they can go different ranges, which is just perfect because we can work on submanifolds, for instance, or on flag data, which is very good in differential geometry, which is important for me. So ultimately here we have data organized as tensors, components of tensors, and applied to geometry. This classification of such data is very important because they stratify the data, they give good approximations of data, which, like you will see here in my talk, are very relevant. Sometimes there are tensors which have very deep meaning. For instance, in Finslerian geometry, the Cartan tensor, it shows how far is the Finsler space from the Riemannian spaces, which are very particular. So a Finsler space can be very far or very close. And this Cartan tensor measures this distance. And this Cartan tensor can be stratified if I regard it exactly as a usual tensor, which can be decomposed by Tucker decomposition. The Tucker decomposition practically gives the core and envelopes in order to regard the tensor as a good collection of data and to see the weight and the refinements and ultimately good classification. I shall use, I don't know if the screen is okay. I shall go on and on. Hopefully I'll manage to, yes, I can. So this is the outline of the talk. We talk about the generalization of eigenvalues, which for tensors obviously have a different meaning because we are talking about n index arrays, not just two like in matrices. Now also here these generalizations can be applied in various fields where significant tensors appear. For instance, we have for Finsler geometry, we have remarkable Finsler structures like Langmuir-Finsler spaces, and we have the corresponding spectral data, which tells us something about the fundamental tensor of the Finsler space, and tells us, and this is more important, a lot of things about the Cartan tensor. And it shows how far is the Finslerian model from the Riemannian models. I want to stress that Finsler geometry in recent years showed its power by extending practical results which were modeled with Riemannian geometry with more general Finsler structures. And these structures were shown to give better models than the previous Riemannian ones. So this extension to Finsler geometry is very fruitful. they give better models. For instance, in Netherlands, Belgium, Astolar and Florac had a very good practical extension in biology. Also, we have other examples, for instance, the Garner-Finsler Z spectra from oncology. And I wanted at the end of the talk to talk about extensions which are nonlinear, like the Finslerian invariant case, which is new. So this is the schedule of the talk. And here is the definition, basic definition of the extension of eigendata, which we know from matrices. So in matrices, we have eigenvalues, eigenvectors, but in Finsley case, we have generalizations of eigenvalues. And here is the typical generalization, which is very used in the Kande-Komparafak decomposition of tensors, which give very good approximations of tensors. And this is exactly what we want when we talk, for instance, in the Cartan framework. That means we talk about a Finsley structure, we build the fundamental tensor, we build the Cartan tensor, and here we are dealing already with the distance from the Finsley structure which we are dealing with the embedded subclass of Riemannian structures. So this distance is, as I said, measured by this tensor, and the Kande-Komparafak approximation shows us a good approximate which says us very much about this distance. Now also, I shall go further here. There is another homogeneous approximation, which is non-trivial in the tensor case. In fact, here we, when solving such a problem, we are dealing with many problems because we have systems of homogeneous, high-order homogeneous equations, and such systems need either a computer approach or a systematic theory which was developed in recent years, and the Kazan specialists from Kazan are dealing with such problems which have systems of homogeneous polynomials equations of higher order. Now, here, I should go further. We have a generalization like an envelope which contains both previous approaches, because we had one approach which is here, which provides eigenvalues, you see the lambda, and the eigenvectors, you see the y. But also there is the second variant, the homogeneous one described before, and here is, you see the lambda, the eigenvalue, tensorial this time, and here is the y eigenvector. What I want to stress here is that we are dealing here with symmetric tensors in this case. A little later, I shall describe how when we go from symmetric tensors to general tensors, we have a strong decomposition which is called HO-SVD, singular value decomposition for tensors. And that one doesn't need any symmetry, and doesn't need, as I said before, the same range through which the indices go. They can have different ranges, the indices. So here we have the two variants, and here we have the envelope. That means an approach which is much more general, and when considering particular cases, we discover exactly the previous particular definitions of extensions for eigendata. So there is an envelope which allows some freedom, and there are two approaches of eigendata, which generalize obviously the matrix case. Now, what is important to stress once again, here we deal with, for the moment, with symmetric tensor. This is a necessity. Fortunately, the fundamental tensor in Finsley spaces and the Cartan tensor are symmetric tensors in the Finsley case. Actually, the HO-SVD which doesn't need the symmetry, is very good for CIJK, the Cartan tensor, in the case when we have something more general than Finsler space. So we have Riemann, we have Finsler, and we have the Lagrange spaces, where already CIJK is not necessarily full of such nice properties, like, for instance, symmetry and so on. So we can deal with this tool, HO-SVD, in more general framework, but for the moment, the Finslerian case is excellent for the Kande-Komparafak, to which goes exactly this kind of identifying eigenvalues and eigenvectors. Now here is the Kande-Komparafak decomposition, as we see here in brief. And here is obviously the error estimation, because the target of Kande-Komparafak is to give a very short, good to compress. Kande-Komparafak gives a compression estimate of the tensor. So an approximate tensor, which is very simply built just from one eigenvalue and one eigenvector, which is practically tensor multiplied by itself. So it's a very simple tensor, which is highly degenerate, but it gives a good approximation of a more general symmetric tensor. So it's good for compressing the data and extracting, obviously, basic features when we go much deeper to recognizing pattern recognition, when we talk, for instance, about area images and so on. So here is the error estimate in the Kande-Komparafak. And here the idea that all this comes from a variational approach, and we have the idea of minimizing the Rayleigh quotient, which comes obviously from much deeper applications from mechanics. Now here we have the metric structures, and what I was saying, that we are dealing here with Finsler structures, which are above here. But we can apply HO-SVD to Lagrange case when we deal with the Cartan from Lagrange case, and further we can go to higher structures, more general. But here, obviously, the information is not so restricted. This is why the results, general results, are not so easy to obtain. But for Finsler and for Lagrange, we can obtain very beautiful results with the HO-SVD. That means the significant tensors of the structure can be decomposed. Practically, they are sliced, and we can practically obtain graduation, which gives ultimately the whole tensor. We talk obviously about HO-SVD here. Now here is something about Finsler spaces on which we focus. And here is the definition of the Finsler space. Practically, it's the so-called Finsler norm, but I want to stress here that the structures which we use are not always having the positivity condition of the Hessian of the square of the fundamental function, f square. So the Hessian of it is basically building a metric tensor, but we can relax this condition of metricity. So this Gij, which is below here, you can see the Hessian of f square. This one is not necessarily positive definite. So we can deal with the so-called pseudo-Finsler structures, which are very used recently in relativity theory. So actually, we have here the classic definition of a Finsler space, but I emphasize that our results are, a large part of them, applicable to the case when the metric is in fact a pseudometric here. I mean the Gij, the fundamental tensor. And this means that this f becomes practically a pseudonorm by relaxing the condition. And of course, in the relaxed case, this fails. That means that this becomes more enveloping, more general. We can have also negative values. And here we have a lot of examples which were studied, for instance, by the Russian group from Moscow, Vyazino. Now here we have some classics. The 2009, when Finsler managed to show its power in applications. So that was the beginning. Until then, to my knowledge, Finsler geometry was just a very interesting tool because the tensors had a lot of indices, of course. They are very specific because they are practically working on the tangent plane, tangent space of the manifold. So they have also a dependence on direction, not only on position, such Finsler tensors. So why extending? That was the question. And here were the first applicative results in 2009, where they said, yes, we have a model and it can be extended. Here is the Riemannian one. You can see it above. This F is basically Riemannian. You can see it from inside. And here it's no longer a norm, it's a pseudo norm. We can focus, of course, on the case when this multiple transvection gives positive results because of the square root, which is okay. And in such a case, Astola and Florak showed that their model in biology was much better confined to reality. So it was tested by real data, and the Finslerian model from below was much better in the modeling results than the previous Riemannian one. So this extension showed itself, so to say, and there are many Finslerian structures which are attempted at some moment to give better models than the known ones. For instance, here in special relativity in subsequent years. And a celebrated norm is Berwald-Moore norm, which is here, the so-called mth-root norm. And here are some practically these come from Grobner bases inside. These are polynomials of which are homogeneous of a specific type. And this goes also to the special theory of relativity. It's an interesting Chernoff model, also known as celebrated. What we know in classic Finsler geometry already, that there are norms which have a deep relevance, mountain pass and Kropina, which was tried to be applied by Ingarden in electromagnetism, and Randers, which is very good for the case when the movement is inside the flow, inside the wind. And it has, for instance, Colin Roberts, Bryant, which insisted on Randers spaces, and more recently a whole book was published by Zhongbin Shan in US, Chinese. And we have also the Antonelli mth-root norms, which were used in ecosystems, practically populations of corals. There is where they started. And here is one deformed version of it. And we have also very interesting Finsler norm, which is locally Minkowskian, and which was very good because it satisfied the relativity EPS, Ehlers-Pironi and Schild axioms. So it confined to a classic model, but it was Finslerian already. And this is why this work, which is quite old, was very good, well anchored in the history of Finsler spaces, because it says, okay, look, such models can be practically made to satisfy classic axioms, so that they have correspondence to deep reality. Now here are the two tensors on which we focus from tensorial point of view and further from decomposition, Tucker decomposition point of view. Here is the fundamental tensor, Gij, metric tensor, and here isCijk, the Cartan tensor, which, as I said, measures, so to say, the distance from the Finslerian structure to the subsequent inner set of Riemannian structures. So it's a distance from a point to a subset in a very relaxed way of saying it. So it's a big set of Finsley structures, and we have one Finsley structure. Inside we have Riemannian structures, and the distance from this Finsley structure to the Riemannian ones is measured here by this Cartan tensor. When Cartan vanishes, we are Riemannian already. We are inside the Riemannian structures, obviously. So the non-vanishing of Cartan is a signal that we deal with a Finslerian structure, proper Finslerian structure. Now we have some properties, and the way in which Cartan is relevant is described very nicely here. What is need to be satisfied if we want a Lagrange space or if we want a Finsley space. So everything comes from the properties of this Cartan tensor. Now further, we have the Kandekon decomposition for G and for the fundamental tensor of a Finsley structure, and further we should talk about the Cartan as well. And here is the shape of Kandekon parafag. This is how it looks for the Cartan case. So we have one repeated vector here, tensor product, and lambda star. Here we raise and lower indices because we work in the tangent space, and here we have a flattened, so to say, perception of components. So we work basically with data components now. And from this point of view, we don't ignore sometimes if the indices are up and down, and we practically choose the components of the vector. And we built the corresponding vector y, and here it is shown that lambda star is a z eigenvalue. We talked about eigenvalues from extended point of view, and here the corresponding one of the corresponding z eigenvectors. So this is why we discussed a bit at the beginning about the extended spectral data for symmetric tensors, because then we can ensure by the eigenvalue and the eigenvector, one of the corresponding ones, a good approximation of our tensor, which tells us a lot about how to classify it, about its features, and so on. Now here is the idea that we can reformulate the eigenvalue problem for these tensors. Here is for J, that means for the metric structure, and here is forCijk, that means the Cartan tensor. And obviously you can see that these equations, the first is trivial because we go into linear algebra of matrices. In fact, we have here nice symmetric matrices which are non-degenerate, but here we have already a proper tensor, and here we can see that the eigenvalue problem is much more sophisticated because the equation already increases in order. So we can see here the second order, and it's a system because we can see n equations. The index I can take values from 1 to n. We have n equations here, with each of them being of degree 2. Of course, when the number of indices in a tensor increases, then we have a larger system, and the order, polynomial order inside, increases as well, and the complexity of the problem is very non-trivial. We need computer already. So here we have some properties which are used, and essentially it's about homogeneity, which is basic in Finsley geometry because we talk about directions, not of vectors. So we work, in fact, in the projectivized space where the directions matter. And this is why the invariants with respect to homotety are very crucial. And here we have some good theorem. Now here is the first example, which comes from the physics of monolayers, nanotechnology. And here is a small explanation which is the phenomenon of upper-lower layers, in which the interest is in separating one layer full of qualities which lies on a second layer, which is the carrier. So when we do that, we are very interested in examining what happens at the contact surface, how they separate and so on. In such a context, we have a Finslerian pseudometric because the signature is not plus plus plus, it's 3D here. So it's not a proper norm here, Finslerian norm, but a pseudo norm. And here the values can be positive or negative. And this is just formal. This is the Lagrangian typically because we see a minus here. So this is just the notation, so to say, it's L. So this can be positive or negative. And obviously the Hessian is not necessarily positively defined. Actually, it has signature plus plus minus. So we use some notations here. It's a complex of data which comes from applications, and we have here those values which are significant for the applications and around which we experimented the model. When I say we, it's a common project with the specialists from Minsk, Republic of Belarus. And here we focus on the tensorial eigenvalues. Of course, when we have a two-index tensor, we are dealing with G here, and this practically goes to the usual linear algebra eigenvalues. So here is, so to say, get results which can be expected because they go straightforward linear algebra way by eigendata theory, spectral theory. Now, this goes for G. But if we examine the eigenvalue, we see that they are highly non-trivial. And the eigenvectors, fortunately, behave much nicer. We can see them. Now, obviously, we build an orthonormal basis because the Hessian is symmetric. And we perform basically diagonalization here. And we have eigenvalues, eigenvectors, everything goes like in classic theory. But here also we have HO-SVD, which also relies on the diagonalization. So when we go to Cartan, well, here things are completely different because, as I said, look at it, it's here. We are dealing with three indices. And here we have slices. We can see it as a cube in which we have slices. And we have basically indices which correspond to these slices. Like going go X with an index I, say index J or Y, and in depth we go by K, so to say. So we have the nodes, yeah, inside the cube if you want. And these are the components of a 3D tensor. So this is Cartan, in fact, the Cartan from here. And here are the slices. You can see the first slice, second slice, third slice. Each slice is a matrix. So we have a 3D matrix practically. It's a an array. Actually, it's a tensor with three indices. So here we have the description of the Cartan tensor by slices. And we go and go and go in order to get Kande-Komparafak, and of course the HO-SVD, which helps us in classifying the Cartan tensor. So here are the equations in Cartan case for the eigenvalues and eigenvectors. And here they are. Yeah, we have the eigenvalues, Z eigenvalues. Here is a double equal. It's just one. So lambda 1, which is the zero eigenvalues, but the corresponding eigenvectors. And we see the difference towards the real usual two-index case, because here we have a very interesting family of eigenvectors in the tensor case, like here. So we can see a lot of eigenvectors. Now also we have the eigenvectors here. And we have some freedom, of course. And we have the Kande-Komparafak, which goes below. Now here we have the system in the homogeneous case, which gives, as expected, different results because the approach is different. So this is good because of evaluating the weight of the Cartan tensor. And obviously here is the idea of getting the HO-SVD, and here is the idea. And here S is obviously the core tensor, which retains most of its features. And here are the three matrices this time, which allow us to obtain the core tensor. Now, the second example comes from oncology, from dynamical systems. A Finslerian metric is built, which models the evolution of the system in a certain way. We have here a least power LSM. Practically here we have least square method accuracy. We have a statistical approach, and we build this tensor from statistical data. So here we have the Euclidean norm, and here is a deformation which is given by a one form. That means a form of order 1. So it's like saying that here we have the norm which is deviated in this Randers structure. So basically this is a Randers norm, and we have a Finslerian structure. So for this Finslerian structure we have obviously built a fundamental tensor, the Cartan tensor, and our concern is, as usual, to see how far is this Cartan structure given by the Finslerian structure from the closest Riemannian one. So how far is it from classic approach, so to say? And if it provides, of course, better modeled information from theoretical point of view. This is the second goal, of course, main goal. If the model is fit to the reality. This is why we have a statistical approach. It comes from reality by building this structure. Now here we have the two frameworks, and both of them are legitimate. Here is mishap. I see at compilation we have a problem. Here, in fact, is a transvection with the metric tensor. And yeah, it repeats. It's practically a transvected version of Z. And here is without that transvected version, so it's the place where the metric tensor may appear in order to lower an index. That's the big idea, because Cartan is covariant, but in the right side of the extended spectral approach, we have a vector itself, which is contravariant. So in order to lower, we have two possibilities. Basically work flat, like in statistics, or work geometrically with other elements when we lower the upper index of the vector by means of the metric tensor, Finslerian fundamental tensor. So there are these two approaches. And here we have some details on how we tabulate the eigendata. We build a Finslerian harmonics for different directions, which are flag directions, because we are working in a tangent space, but we have always x and a y star. That means a basic direction. This is why it is called a flag, because the rest of the y, the data, is variable, so it's in the tangent space, and here we work with the y component in Finslerian spaces. But a y star, that means a basic direction, is always inside the objects, the tensors, for instance, in our case. So this is why, based on this flag, x and y star, we build the whole machinery around in the tangent space, which is kind of flat machinery, like in the classic n-way array approach. So it's basic, so to say here, nothing very special, but it confines to the Finslerian background, where all the objects depend on position and direction, y star in this case. So y1, y2 are pointing to different positions on the indicatrix, which is Finslerian. You can see an ellipse. Remember, it was all about deformed circular one, so it is an elliptic one in this case. So we have some examination of how the eigenvalues look. They can be real or complex, so we can examine the imaginary component and so on, and see what happens to them in order to investigate what is important here, the weight of the tensor. This is the goal ultimately. Now here is the Euclidean framework, and we had a lot of results here added to strong results which are here at the beginning. Our was just a bit more geometric. Here it's all algebra of n-way arrays. Yes. And also we have the other approach, which is metrical. So you can see it here, where the metric G, Finslerian one in our case, applies. And here is that. Here is the first approach and the second generalization, two different generalizations. Each of them has its qualities, each of them provides eigenvalues, but with different meanings. Now here is the Finsley geometry application. That means how this framework fits onto the proper Finsley framework. And it's important because we have two directions. One which is assumed fixed and which enters the object, the so-called flag. So we have there the x and the y, which is inside the tensor. And by its indices, the tensor acts on the tangent space and practically acts on another vector y with its counterparts for each index goes practically another possible y. We have a multilinear form when we talk about tensors as usual, but they depend, these tensors, very special, they depend on position and basic flag direction. This is the difference. And this is why in Finsley geometry we wonder what happens if when we act, because it's a symmetric tensor, on one vector, we have also a vector in the flag. What happens if they coincide? And the result is astonishing because at the homogeneity, we have a very poor structure at the first side, but if we add some conditions, we get interesting results regarding the indicatrices. Now here is the idea of indicatrix when applied to Cartan tensor. And here is the idea that this extends when we have a tensor approach with interfering metric structure, like here, for instance. And here is just a little list of applications, which are very wide, and many open problems, which expect to be solved. And I want to stress out that the references, I started, sorry, with my name, but it's just somehow alphabetic. And we have a lot of citations here, and I'll be more than happy to provide much more literature, which I have tried to read. And we have from different countries a lot of conferences which appeared, but mostly the one which is itinerant and which is focusing on the n-way approach. Here I also included in the references some MATLAB resources. And here we have an Tucker HO-SVD package and toolboxes and laboratories for those who are interested by this field. I will be ready to discuss with anyone who is interested. Here I have an announcement. We welcome you to Romanian, as you like. If you want to come to us, please be our guests like tourists, but we try to make it online. That's the idea. It's a conference. So it's in summer, end of August, and it will be online. We have it already on this side displayed. So we welcome you at this conference, and if Professor Prișleag will agree, I shall transmit to him a formal invitation in order to disseminate to those who are interested in our Conference on Differential Geometry and Dynamical Systems. Thank you very much for your attention.
Thank you very much.
Little question.
Some small comment, please. Alexander Mednych. First of all, Vladimir, thank you very much for a wonderful talk. So many unusual applications, so many good mathematics involved in this consideration. But maybe I want to say one more possible implication inside of mathematics. If we consider a very simple problem, for example, tetrahedra in non-Euclidean geometry, and want to find the center of gravity of this guy. As a result, we have also some agent problem for tensor, non-trivial tensor problem. First of all, from the first point of view, very elementary problem, and the solution is, in some sense, like in technique you're shown in your lecture. Just some of the possible applications. Very simple one, but also useful. Okay,
Yes.
Thank you very much.
Thank you.
May I ask a naive question?
Yeah.
Ricci tensor in Einstein equation for gravitation is metric or Cartan tensor? Do you know?
Actually, we use in relativity, as known, the curvature tensor R and its transvection, which is Ricci already, and the scalar of curvature. And Ricci and scalar of curvature appear directly in the Einstein equations.
Thank you. Thank you.
Welcome.
Any other questions? Maybe.
And sorry, do we say about operator presentation, for example, Hamiltonian, is equal to tensor presentation as Cartan or symmetric tensors as symmetric operators?
The idea is that we are dealing here with the approach in which we deal with tensors which are covariant. The covariance here is an essential question because if we work on the tangent space, we have usually Lagrangians. You saw we talked about Lagrangians, but if we go to the dual space, T star cotangent space, we are dealing with Hamiltonians. And between them, we have the Legendre transformation. So we are focused on Lagrangians here. By Legendre, we can move to cotangent space to Hamiltonians. Yes.
Yes. Thank you very much. Thank you.
Welcome.